So, welcome back friends. So we were looking at the very interesting concept of Majorana fermions in the previous lecture. So, what we deducted was that Majorana fermions are real solutions. So far what we have learned about them is that if I take gamma matrix to be completely imaginary, one particular example is what is given by Majorana essentially, but this is not unique. Okay, this is not unique, and so and if you take this particular they are completely imaginary, the gamma matrices are completely imaginary, you end up having um, representations in which psi is equal to psi star. But you can also, but because this is not unique, what you do is you introduce a unitary transformation under which all the gamma matrices are related to each other. So all of them give you the same solution, so they are not unique. So this unitary transformation is represented in this particular fashion where u gamma mu tilde u dagger essentially. If that is the case, so the condition on the spinor, on the Dirac spinor comes out to be psi is equal to u psi tilde, or the Dirac wave function comes out to be psi is equal to u psi tilde. So if that is the case, the reality condition that psi tilde is equal to psi tilde star, the solutions should be real. That is the original condition which we got because all the u's are imaginary. So you end up having the condition that psi is equal to uu transpose psi is equal to uu transpose psi. Just give me a second, I am just unable to move this. Yeah, so uu transpose psi star, essentially uu transpose psi star, because a general unitary matrix uu dagger is equal to 1, but uu transpose is not equivalent to 1. Now uu transpose, I define it as some other matrix gamma 0 times c. C is, as we will see, is a very important operator which is a unitary operator, okay, which is a very important operator which is a unitary operator which is called as a charge conjugation operator. And upon acting upon this operator, I define the solution to be psi c, essentially psi c. Okay. So psi c is equal to gamma c psi star, essentially gamma c psi star is equal to psi c. So the original Majorana condition that psi tilde is equal to psi star, or the real condition, just becomes psi is equal to psi c. The real wave function condition just becomes psi is equal to psi c. Okay. Now this condition is very interesting and very nice, and but we were looking at implications of this, essentially what does this imply, that now this operator psi c operator, what does it do? The c operator takes particle wave functions to anti-particle wave functions. This is what we will see just now essentially, and then the particle quantum numbers, okay, the particle quantum numbers will become should be equivalent to the anti-particle quantum numbers. So psi is equal to psi c implies, this is what implies essentially, okay. Okay, this is what is, it implies that psi should be equivalent to psi c means, okay. So now what does now under arbitrary representation, essentially under arbitrary representation of the gamma matrices, so what does the psi represent essentially? So psi, if we are taking to be u and v wave functions, what does psi c do, not psi essentially. So the first implication, what I want to see, the first implication again, the second implication is that it implies that the particle quantum numbers and anti-particle quantum numbers should be same. That is only possible when electric charge of this particle should be equivalent to 0, okay. This will see, so this condition, the Majorana condition, is satisfied in real world only by neutral particles essentially. So so that means the electric charges -1 should be equivalent to +1. So that is only possible when minus q is equal to plus q, it is only possible when q is equal to 0. So, examples of such particles are the neutrino, which we just saw, and neutron, and so on. So, essentially neutrons are also. Now, let me also spend some definitions on the C operator. Action. How does the C operator act essentially? So, the C operator acting on wave function V SP spin and everything is equivalent to C U P S star. So, the charge conjugation operator acting on U star P S will take you to an antiparticle wave function essentially. So, it will take you to an antiparticle wave function. Similarly, you have a very equivalent relation U S P, the spin and everything essentially should be equivalent to gamma 0 C V star of P S. Okay. Now, if I take gamma 0 to be in the Majorana representation, so what it means, and U and V, okay, this is the general definition of the operator of general definition of the operator C. So, under the operator of C, action of C, V takes it into U star gamma 0. These are different wave functions in general essentially. Okay. Now, U and V's are different wave functions which are related by the action of C operator essentially. Now, U is equal to, now if V is equal to U star, okay, this is in general, but for the, this is also true for the Majorana representation. This tells you when C is in the Majorana representation, C is in the Majorana representation, okay. In the Majorana representation, you see that U and V are no longer independent, but just complex conjugates of each other. So, now this is a bit crucial to understand that under the action of C, so under the action of U, wave function gets transformed into a V wave function, okay, the U wave function gets transformed under the V wave function. In the particular case of the Majorana representation, okay, in the particular case of Majorana representation, okay, this just means that gamma 0 C is essentially, but you see essentially gamma 0 C we just defined, this is exactly the same as the condition of the Majorana condition. Essentially we have the upper condition as the Majorana condition essentially. In general U will U star, so that means U the left hand side also will be U, and the U and V are nothing but complex conjugates of each other essentially. U and V are nothing but complex, V is nothing but U star, okay, and U is nothing but V star essentially. That is what it means, that they are no longer independent, they are complex conjugates of each other essentially. Now, under the matrix gamma 0 C, under the condition that these wave functions are Majorana wave functions, okay. Now, in general, okay, this is for Marana representations essentially. So for the this is exactly what is happening for the operator under Marana representation. Now in the Dirac representation things are different. Now we will come back to that in a second, we will come back to that when we need the case or complex conjugate. Now what happens, if I can just complex conjugate. So this is an important thing, that this sets you the first implication that the particle and antiparticle wave functions are complex conjugates Now this will reduce the number of independent degrees of freedom in a Dirac equation from 4 to 2, because this will reduce because the antiparticle wave function is not an independent wave function anymore, it is just the complex conjugate of the Dirac wave function, of the complex conjugate of the particle wave function. Now let me just make it much simpler. Essentially we have seen that let us understand this in terms of Weyl fermions. Essentially to make life easier, let us understand this in terms of Weyl fermions. So then things become easier. Now in terms of Weyl fermions, so let me call it as psi L psi r, because I told you that this can be written in terms of psi L plus 0 psi r. I think we wrote for the massless case we can write it in this particular case psi L and psi bar, and this is true also for massive case, which is this is also true for the case of massive Dirac spinor, where psi L is equal to 1 minus gamma phi by 2 times psi are not helicity states, but chiral states, where psi L and r are not helicity states, but chiral states. If that is the case, so the Weyl equation is modified as these are the equations which we wrote initially essentially. So these are the equations we wrote it down. So E psi r is equal to P dot sigma psi r minus M d psi L. then you have E dot psi L is equal to minus P dot sigma psi L plus sorry, this also will be minus M d psi r. Now, M is the same M as previously. This is what we wrote down for the while equation. So, let me just check the notation what I introduced. I am just rewriting this equation, chi 1 chi 2 I wrote down, but instead of chi 1 and chi 2 I am writing it as chi L and chi R. Okay. So, but with massive. So, chi L with minus sign, okay, chi L with minus sign. So, this is precisely what I wrote down, but now with the mass term given in this particular fashion. Now, realize that M d is the Dirac mass term, M d is not equivalent to 0. So, these are chiral equations, these are nothing but your chiral equations. I just rewrote the Dirac equation in this particular fashion. So, the Dirac equation is nothing but I M d psi, and I expanded psi is equal to psi L psi R no psi R psi L I think. Okay. And this gives me these equations. Okay. I expanded them in terms of these equations. Now, let me put, this is nothing but your original Dirac equation for massive particles essentially. In the limit m goes to 0, you get back your chiral equations. In the limit m goes to 0, you get back your Weil equations. Now, why I introduced m is equal to M d, because I want to make a small modification now. I want to make a small modification now. Now, I want to introduce the condition that psi c is equal to psi. The Majorana condition. So, I want to introduce the Majorana condition. Okay. In this case, the Majorana condition, okay. Now, I introduce psi is equal to psi c. Now, psi c is equal to there. Now, before going further, I want to introduce a interesting relation that c is equal to I gamma to gamma 0. Okay. C is equal to is the representation of the charge conjugation operator in Dirac representation. So, we are doing everything in Dirac representation right now. So, because we want to see what happens in the Dirac representation after introducing this thing. Now, the operator C, I said it is a unitary operator, it is complex essentially, and so this has this form essentially. The operator C is this also I mentioned to you in the previous class that C can be written in terms of the gamma matrices. So, I gamma 2 gamma sigma, okay. Substituting this in terms of the sigma matrices of the thing. So, you end up having the relations, substituting this we have E psi r minus P dot sigma is equal to P dot sigma psi r minus M r, okay, sigma 2 psi r star, okay, Now I will tell you why there is because now the equations are no longer decoupled, they become MR star essentially. MR star is essentially to distinguish between the left mass and right mass, and E psi L is equal to minus P sigma dot psi L minus I ml sigma 2 psi L star this is nothing but your Majorana condition essentially. This is nothing but okay, this is nothing but your Majorana condition, okay, written in these are the Majorana equations for Weyl fermions essentially in Weyl or chiral representation essentially, or chiral or helicity representation. So these are Majorana equations. Now see this, the first equation psi and psi star appear in the same equation essentially in the mass, okay. Psi and psi star appear in the same equation, okay. And now in the limit mass is equal to 0, you get back your MR is equal to ML and is equal to 0, you get the same equations are same. But if the mass is different, if ML and MR are different, because I introduced MR as a different mass for the right fermion and ML as a different mass for the left fermion essentially, should these two masses be same essentially, should these be masses to be the same, okay, in general. In general, okay. So what we have is Majorana fermions of two component Majorana fermions which are right moving, which are solutions of the first equation, okay. They are particle and the antiparticle is the same as the particle essentially on the top of the thing of the Weyl fermion, and the left particles are this particular case essentially, okay. So one should recognize that the mass is 0, then okay, they are exactly the same essentially, they are exactly the same and the mass is 0, and so you cannot couple them to Dirac fermions, and if you write a current for the Majorana fermions it just becomes 0. Now Majorana fields in 4 component form are given as psi L is equal to I sigma 2 psi L star psi L, psi R is equal to psi R I sigma 2 psi R star. So both upper component and lower component are same, it is the same wave function sitting in the upper component, and this is called 4 component Majorana fermion. This is not equivalent to a Dirac fermion, okay. This is not equivalent to, okay, a Dirac fermion. So but there are some interesting concepts essentially. Now you see that what we have seen, okay, let me just repeat. Now you see that we started with the Dirac equation in terms of psi L and psi R, and we see that psi L and psi r bar psi L plus psi L bar psi r is the MD term, essentially. Now what happens is psi E is equal psi is equal to psi C, essentially this condition, this modifies these equations essentially. You can just put this back into psi is equal to psi r c and everything, and use the condition that psi is equal to C is equal to I gamma 2 gamma 0 essentially. Okay, C is equal to I gamma 2 gamma 0, and gamma 2 gamma 0 do not use the Marrano representation, just use the Dirac representation, but use the condition, the Marrano condition, that psi is equal to psi c, Putting this back into the Dirac equation, you end up having two independent equations with it in general can be different masses, but if they are from the same mass, Mr is equal to Ml. If Md is equal to Mr is equal to Ml, it can be, okay, if Md, but in general these are your independent Marrano fermions, these are different equations. Essentially you see that they have IMR sigma 2 it is a mass, essentially psi star sitting here, essentially these are real fermions, these are real equations, and these are real solutions for this equation essentially. You can write them. So these are two component independent Marrano fermions, which, and there can be two kinds of Marrano fermions, one corresponding to psi r and one corresponding to psi L. Okay, and here, okay, and the psi r these are real solutions, that is the reason they are only so they are psi is equal to psi star, so they are still two component, but the solutions are real, remember that. Okay, so so one is so if you solve this, essentially this gives me for a mass, in the limit mass goes to 0, they go back to your Weil fermions, Now the funny thing is, no, this I will say it now, essentially this is the most general. Okay, here I considered MD not equivalent to ML MR. In general they are, okay, here when I wrote these equations I wrote that assuming that they are not equivalent to each other, but this is just from substituting that, you can substitute it and find out this solution. This can be left as a homework essentially, I want all of you to do it. Okay, so just check that you get these equations, these are straightforward, just using the psi is equal to psi c condition. Psi is equal to psi c, this condition, just you get it, use psi is equal to I sigma 2 gamma 2 gamma 0, sigma 2 gives you this sigma 2 here, which is present here essentially. Now you can write 4 component Marrano fermions, but you see the upper component and lower component are not independent of each other essentially, and they are complex conjugate representations of each other, they are not really independent representations. So the upper 2 component and the lower 2 component are complex conjugates of each other essentially, and similarly psi r is equal to this one, psi r I sigma 2 psi r essentially. It is like writing real fields in terms of complex entries essentially. This is real wave functions in terms of complex wave function, that is the complication which we are seeing essentially. Now funny thing is, one last thing which I will leave here, and in the next class we will see other thing. So 2 Marrano fermions ML, same masses, 2 Marrano fermions with same masses, and form a Dirac fermion. Now this is the problem is this notation here is slightly complicated because the moment I use psi c is equal to psi, I still using the Weil fermion notation. The solutions of this equation are real, the solutions of this real the solutions are, if I want to still use this one as in the same Weil like notation, the things become complicated, but I can still use real solutions as the real wave functions as the solutions essentially, because I get real wave solutions of the wave function. But I still want to stick to the psi L and psi R's because that notation, because I have something else in my mind is because I want to connect it to neutrinos, I want to connect it to something else and something the reason, that is the reason why the Marana fermions becomes complicated in most of the time essentially, but otherwise they are much simpler objects. Okay. These are just real solutions. If you solve these equations, so let me call this solutions to be some psi chi or chi 1 or chi 2 say, or sigma 1 or sigma 2 or something essentially. Now take these two sigma 1 and sigma 2, okay, the solutions of these two, these are two Marana fermions and take they have independent masses. So they have independent masses, one has m1. Now imagine that you have the same masses, two Marana fermions with same masses and they have opposite chiral, the one of the chiralities is psi L is psi sigma to psi r star, they can form a Dirac fermion essentially. So you can always combine two Marana fermions and form a Dirac spinor, but a 4 component Marana's representation is not equivalent to a Dirac fermion essentially, because it is the same field sitting here, okay, it is the same field sitting here on the top and the bottom. This is the Marana representation, 4 component Marana representation, and this is called the 4 component Marana representation. So this is called the 4 component Marana. Now if these are different fields on the top and bottom, you get back your Dirac equation with the masses to be same. These are two different Marana fields on the top. So two Marana fermions can form Dirac fermion. So Marana fermions are they only have 2 components, so they only have 2 degrees of freedom. So what are these 2 degrees of freedom? They have only the left or the right movers, essentially are the right movers, their particles are equivalent to the spin projections are either left or right because they are massive, one can be moved to another, because remember that you should not think in terms of Weil fermions, Marana fermions. So there are 2 degrees of freedom, one can be left and another can be right essentially, but they are their own antiparticles essentially, there are their own antiparticles. Okay, these are the 2 degrees which you can construct these Marana fermions depending and one funny thing is that 2 Marana fermions can form a Dirac fermion, okay, 2 Marana fermion. Now I know this could be lot overwhelming, but if you get a gist of this, I think this is useful, and in the next class I will try to do some applications in condensed matter physics and in high energy physics, especially related to neutrinos with respect to Marana fermions. So I will stop here and we will continue doing this one more class on Marana fermions and then we will move to something else. Okay. Thank you very much.